Jan rolls a fair die 10 times. The random variable x represents the number of times the die lands on a 6, and we're asked to use a suitable distribution for x to find these probabilities. This is shouting out for a binomial distribution. 10 trials, probability of success is going to be 1 over 6 because, yeah, fixed number of trials. We have a fixed probability because it's a fair dice. It's going to be independent events because as you roll the dice, it's not going to affect the next roll. And then finally, there's two outcomes. You can either get a 6 or not get a 6. So this is a good model to use. Now, if we want to find the probability x equals 3, the quick way is just going to be to put it into our calculator, go to menu. I'm using the old ClassWiz calculator, just prefer it to be honest, and I've kind of realized that this emulator can deal with it, but you should be able to find it on the newer one if you're using that. So distribution, I'm doing binomial PD here, because it's just an equals, and then I'll just go with variable for one value, putting in 3, and then 10, and then 1 over 6, and we get 0. Sorry, we get 0.155. Maybe write down a few more figures. It's actually a 0.4, and then I'll round it. Now, I do want to really emphasize it's important to know where that came from. So I'm going to talk about it. Right, if we have 3 successes and therefore 7 failures, we can imagine a scenario where, well, we get the first 3 as successes and then the next 7 are all failures. So as we multiply down the tree, the tree line was just a way of showing it, but basically you multiply your probabilities together. So it'd be 1/6 to the power of 3, and then 5/6 to the power of 7 for that particular arrangement. And then we just bring in the idea that we can swap them around and we'd still be getting 3 successes and 7 failures. So we need to think about how many different ways to arrange 10 objects. Well, that's 10 factorial, but in which 3 of them are the same. So I need to divide through by 3 factorial to account for that because every single, if I swap these two around, I'd get the same one for like every kind of situation with SSS in, I could swap them around. And then the same for the 7f's, I would divide through by 7 factorial. And this ends up becoming 10c3. That's 10 factorial over 3 factorial, 7 factorial. And if you type that in your calculator in full, then you will get that same answer. But please don't just accept what your answer's given you, what your calculator's given you. Make sure you understand it. I'm not going to go into more detail on it here, but this is the underpinning idea. For probability x is less than 3, it's going to be that x is either 0 or 1 or 2. And you would add those together. Now, this is a scenario, as long as you understand that's the main thing, this is a scenario where you definitely want to use your calculator. You're not going to find the 3 separately. So now we return to distribution, but this time it's going to be binomial CD and variable again. So I'm going to put a 2 here, and then we get 0.7752. So this is probability that x is less than or equal to 2. That's the value I have to put in, 0.77522 or 0.775. Job done. Jan repeats this experiment each day for 60 days and records the number of days when x is equal to 3. Find the probability that there were at least 12 days when x was equal to 3. So this is actually a new binomial distribution because now there are 60 trials of the 10 times. But the probability of getting success, the number of days when x is equal to 3, is going to be that answer we had in parts A1. Now I'm actually going to use the non-rounded version up to 5 decimal places, but you get away with using 3 decimal places. I'm just trying to be as precise as I can. So then I want the probability that y is going to be at least 12, so greater or equal to 12. But in my calculator, unless you've got a graphical calculator or one that deals with greater or equal to, I'm going to need to do a 1 minus. So I want 12 or more, so I need to minus 0 to 11. Minus probability that y is less than or equal to 11. By the way, that's the same as minusing the probability that y is less than 12, if you prefer to think of it like that. So back to our calculator. This time I can still use the CD button, but it's going to be 11 here. I've got 60 trials. The probability of success is 0.15504. and I get 0.78822. But remember, I'm doing 1 minus that. Now it will be stored in my answer button, so I'll just go to 1 minus answer and get 0.212. Okay, so it's a binomial distribution within a binomial distribution. An estimate for the total number of sixes that Jian will roll during these 60 days. Well, he rolled the dice, or he or she rolled the dice 10 times for 60 days, which means in total 600 rolls were made. And the probability of getting a 6 is 1 over 6. That means we would expect one out of every 6 of the rolls to be a 6. So this is how you can find it's called the expected value actually, but it's the same thing, an estimate for the total number of sixes. We're expected to get 100 of each number. Doesn't mean we're going to, of course. We've got probability involved, but that is what we would, that's going to be an estimate. That's what we'd expect from the 600 rolls. And finally, we're asked to use a normal approximation to estimate the probability that Jian rolls a total of more than 95 sixes during these 600 days. Okay, so I'm going to first of all construct actually another binomial distribution, then I will do a normal approximation to it. But let's just set it up. So A now will follow a binomial distribution. So it's the total number of sixes over the 60 days is going to be 600 trials, again, just like in part C. And the probability of getting a 6 is again 1 over 6. So we want the probability that A is more than, so greater than 95. Well, I can say that A is approximately another distribution, um, and maybe I'll call it C. I'm just trying to avoid using X. I've already used X and Y. These were distributions. Now I've got A, now I've got C. Sorry if the letters are complicating, but I need to just make sure that they are different distributions. Right, so now I've got my normal approximation. So we're actually given in the formula book that the mean is equal to NP. That's the number of trials times the probability. That's our 100 from the previous part. That's what we're going to expect. And then the variance is NP times 1 minus P, which in this case is going to be 100 times 5 over 6. This ends up becoming 250 over 3. Now, when I write it in, I like to write it so I don't forget to get the standard deviation. So I'm going to square root it and then square it, just so I can see that I've got mu equal to 100, and then sigma, that's my standard deviation, equal to root 250 over 3. So now the probability that A is greater than 95 is going to be approximately equal to the probability that C is greater than, wait, we can't just be putting 95 in. We're going from a discrete distribution to a continuous distribution, and we have to do a continuity correction because in a normal distribution, greater than 95 and greater or equal to 95 are the same thing, whereas they're not for binomial. So let's just think about this. I always like to draw some little bars out. I mean, I don't know what the distribution looks like, but here we go. So I'll put 90, like basically I've got my normal distribution and it was a single line, but I have expanded it into a rectangle with a base of 1, so the height remains the same. And I want it to be greater than 95, so actually I want it to start here at 95.5. I'm going to go 0.5 to the right. If it was greater or equal to 95, I would include this and it would be 94.5. But actually I don't want that, I just want this onwards. That is not a comprehensive explanation of continuity corrections, it's just talking about it briefly in this question, but you need to put that in 95.5. Okay, everything is now in place though, ready for our calculation. So back to distribution. This time it's going to be a normal CD. Our lower value is 95.5. Our upper value is just a large number, so let's go with 10 to the power of 9, for example. Calculator can deal with that. I get away with much less if I wanted. Standard deviation. Square root of 250 over 3. Mean of 100. And there we go. We've got there 0.68897. Which I'll then round to 0.689.